Okay, so last section we're going to look at is 11.3, and it's going to start out by talking about the binomial theorem. So basically a binomial is anything that has two terms. That's a binomial. 3x plus 4. 2y plus 5x. What we're going to do with these kind of binomials is raise them to powers. So if you wanted to square that, you'd have to write 3x plus 4 times 3x plus 4 and FOIL. You can't just say, oh, it's just like 9x squared plus 16. You've lost some stuff that way. Okay, you have to FOIL it. Not too bad if you only had to do it to the second power, but if I asked you to do it to the 20th power, now you'd have to write 3x plus 4 20 times and FOIL every pair of them. You might be able to use some tricks to speed it up a little, but the fastest trick we can use to do it is the binomial theorem. Okay, so I'll show you how it works. So what we're going to do is look at a few special cases. Okay. What we're about to look at is some special series. Okay, a few different series. So the first one we're going to look at is a plus b squared. If you do that all out, can somebody tell me what you would get when you FOIL out a plus b times a plus b? Tyler?
A squared plus AB plus B squared.
Close.
AB plus, A squared plus 2AB plus B squared.
There you go. A squared plus 2ab plus b squared. Right? That's what you get if you FOIL it. Now, let's take that result and let's do it again. Let's multiply a squared plus 2ab plus b squared times a plus b. So now we're cubing it. So if we just write it out real quick, distribute the a to everything, a cubed plus 2a squared b plus ab squared, and now distribute the b, plus ba squared plus, so we got 2ab squared, b squared, and then plus b cubed. Okay, so we've got some like terms we can combine, but let's see what happens when we combine it. We've got the a cubed plus the b cubed. We got that. We've got a 2ab squared, and we've got a 1ab squared right there. 2 plus 1 gives me 3. What else do I have? 1ba squared, 2. Wait, did I cross out the wrong one? Yeah, I crossed out the wrong one. So a squared b, right there, a squared b. So we combine, wait a minute.
That's the wrong one again.
Did I do the wrong one again? Having trouble today.
B cubed isn't. Yeah.
How's that? 2a squared b, 1ba squared. Same thing, different order. That adds up to 3. Then you have a 1ab squared, 2ab squared. 1 plus 2 gives me 3, I hope. All right, so we get that. Now, I'm not going to try because apparently I have trouble with just cubing. But if you do it to the 4th power, that's what you get. And if you do it to the 5th power, that's what you get. Okay, I'm more interested in kind of what's happening here. There's a lot of different patterns. Does anybody notice, after looking at these 5, any patterns when you do it out? Yeah? The constants are doubling. Are you talking about the coefficients?
Yeah.
There is something with the coefficients, but they're not doubling, yeah. Does anybody see what the coefficients are? So in the first one, it's 1, 2, 1. In the next one, it's 1, 3, 3, 1. And then 1, 4, 6, 4, 1. and then 1, 5, 10, 10, 5, 1. Those are from something. Anyone remember what those are from? Yeah?
Pascal's triangle.
Those are the numbers from Pascal's triangle. Okay, if you look at it, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So what ends up happening is the coefficients just come from that triangle. A couple other patterns. If you look at, let's just look at this one. Look at the A. It starts out a to the fourth, then you get an a to the third, a to the second, a to the first, and then the a is gone. And with the b's, it's just the reverse. There is no b, and then b to the first, b to the second, b to the third, b to the fourth. So it's like the first letter starts at the highest power and goes down. The second letter starts at the lowest power and goes up. If you add the exponents together for any term, there you have a 4. 3 plus 1, 4. 2 plus 2, 4. 1 plus 3, 4. Okay. The exponents on any term added together will always add up to the original exponent. What else? How about the number of terms that you get when you expand it out? Anyone see a pattern there? Yeah, Jayden?
So is that number plus 1?
Yep, you always get n plus 1 terms, where n is the power. So if you cube, you're going to get 4 terms. If you square, you're going to get 3. So we can write some of these down. So we just said that one is n plus 1 terms. The sum of the exponents on each term is n. Okay. The degree of A goes down by 1. The degree of B goes up by 1. And we answered this last question. Where are the coefficients actually coming from? Pascal's triangle. So what that means is if you want to expand something to a relatively large power and you don't want to FOIL it all out, all you need to do is follow the pattern. The only hard part is this. You have to have the row in Pascal's triangle. So if you wanted to expand something to the 10th power, you would need the 10th row in Pascal's triangle. That in and of itself might be a little time consuming to figure out. 10th row wouldn't be too bad, but let's say I wanted you to do something to the 50th power. Well, writing Pascal's triangle out all 50 rows, not the best way to do it. So there's an even faster way to get the coefficients than Pascal's triangle. In fact, you could tell me, you could say, you know what? I want to know what coefficient would be in row 300, column 76 of Pascal's triangle. And I can tell you. Give me about 2 minutes, I'll do it out, and I can tell you what it is. But there is a way to find any number you want in the triangle with a formula. Okay, and we'll get to that. Okay, so Pascal's triangle basically starts out with 1 at the top, and then going down on the kind of the outside edge of that triangle is all 1s. And each number is the sum of the 2 that are directly above it. So 1 plus 3 gives you 4, 3 plus 3 gives you 6, and so on. Oops. Okay. One thing we have to kind of keep track of is where we start counting. So with Pascal's triangle, you always start with row 0, column 0. So that number that I just circled is row 0, 1, 2, 3, 4, row 5, column 0, 1, 2. That's row 5, column 2. And we have a notation to write that, row 5, column 2, and I'm going to show you that in a minute as well. Okay, so I did Pascal's triangle out to the first 6 rows. Not too bad up to that point, but again, if you're going to go like 15 or 20 more rows than that, it's going to start to get a little kind of unwieldy to deal with. So some patterns here in the triangle. Each row begins and ends with a 1. Each entry is the sum of the two numbers above it. Okay. There's all kinds of patterns in this triangle. I think if you look at rows that are prime numbers, there's a special pattern. And I think the pattern is that every number in that row is a multiple of its row number, but only on prime rows. So if you look at row 3, 3 is a prime number. Every number in row 3, except the ones, is a multiple of row 3. 5 is your next prime number. Every number in row 5 is a multiple of 5, except the ends. Row 7. Every number in row 7 is a multiple of 7. Okay. That, of course, doesn't work for rows that are not prime because every number in row 4 is not a multiple of row 4. Okay, you got a 6 or a multiple of 4 because of that 6. Okay, there's lots of interesting patterns here. So, if you want to know what the coefficients would be to expand a binomial to the nth power, all you have to do is look at the numbers in the nth row. That's it. That's where the coefficients come from. Okay, so we'll start out just by practicing expanding a few binomials, but then we kind of want to get to the point where we could say, all right, what number would be in row 26, column 13? And that's one of the last things we'll do. Okay. Any questions on Pascal's triangle? All right. So when we start to expand, we'll start with something pretty simple. Okay. We'll start with something like x plus 6 or something, or y plus 2 to the 5th or 6th power. Okay, so we'll do a plus b to the 6th. So first thing I need is, I'm going to need the 6th row in Pascal's triangle. I already have it. It's right there. So let's start with our terms. Okay? What's going to be my first coefficient from row 6? Jess? 1. So you really don't need to write it, but we'll write it. So we got 1. And now, am I going to have an A in this term? Yes. Am I going to have a B? No. We're just going to have an A. What's the power going to be on the A? Yeah, it's going to be 1a to the 6th plus. So I guess this kind of ties in a little bit with a series because you're adding up a bunch of things. But other than that, that's really the only connection. Okay, what's going to be my next coefficient? Jess? 6th. Now I'm still going to have an A, but what's going to be the power on A now? Yeah?
5.
It's going to drop down 1. And the power on B, well, it's going to come up 1. So I'm going to run out of space, but I'll just go below it in a second. So that's my second term. Felipe, you think you could give me my whole next term?
15, a to the 4th, and then b to the 2nd.
Yep, b to the 2nd. Ariana, my third term?
20a to the 3rd, and b to the 3rd.
Yep, 20a to the 3rd, b to the 3rd. And now we're at the point where once you reach the halfway point in the triangle, the coefficients are a mirror image of the ones that came before. So now we go back down to 15, a squared, b to the 4th. Then we go to 6, a, b to the 5th. And the last term is 1b to the 6th. Okay, so that's what you would get if you would expand it, and that's way faster than trying to FOIL that all out. Because as you can see, it's easy to make mistakes, even with powers that are smaller than 6. Okay. Any questions on that? Okay, so let's try one that's a little harder, but when it starts to get harder with things in the parentheses, I usually make the exponent outside smaller. So let's try
This right, I have to leave the filter.
So let's try 2xy to the fourth. So this time you only need the fourth row of the triangle. So what I can do, if everyone has example 1, I can delete it and then pull the triangle back up. Is anyone still copying example 1? Okay. All right, so now we need row 4. Now, when you do it, anytime you have something that's a little more complicated than a single factor inside the binomial, keep it in parentheses. So what I underlined in red, that's like my A. And then what I underlined in black, that's like my B from the last problem. Okay. All right, so let me start you off with the first term. So we've got 1 times 2x to the fourth power. Okay, plus. Nick, could you give me my next coefficient? Yep, so row 4, we've got 4. And what's the power on 2x going to be?
3.
3. And now y to the first. Okay. Devin, can you give me my next term?
6, 2x to the second, y to the second.
Y to the second. Tanner, my next term?
Or 2x.
4 times 2x to the,
To 1.
yeah, so the first,
Y to the third.
y to the third, and then the last one is just 1 y to the fourth. Now, because we have these monomials that have 2 factors in them, we have to do that out. So basically, you think of those as both having an exponent of 1. Each one of them gets the exponent. So what's 2x to the fourth power? Yeah.
16x as well.
Yep, so 16x to the fourth plus, we're going to have 8x cubed times 4. What's 8 times 4 give me? Scott? 32. So 32x cubed y plus, what's 2x squared times 6?
12x squared.
Careful, yeah, 24. X squared. I think you said 12. I'm not sure. And now the last one, well, second to last one, 2x, it's just to the first, so you don't have to do anything with that. But you got to do 4 times 2 gives you 8xy cubed. And then the last one, there's nothing to do, just like the first, well, the first one had a little bit to do, but the last one's nothing. Just y to the fourth. Okay, now if you had something like this and you had to work backwards to figure out what it came from, that can be a little tricky. I mean, you can tell that it should be to the fourth power because you've got 1, 2, 3, 4, 5 terms. So you know it was something plus something to the fourth power. And I think if you focus on the first and the last term, that would probably be the easiest way to figure out what you had originally. Because you know that is just a single term by itself, and that was a single term. It didn't involve both what was underlined in red and black. So that would kind of help you if you had to work backwards. All the other ones in the middle are kind of a mixture of some parts of the red and some parts of the black all multiplied together. So it's kind of hard to separate out what was going on there, or can be. Okay, any questions on that one? Let's try one more like this. This time the power is a little bit lower. This time just the third power. But it's not set up quite the way the other two were. It's supposed to be something plus something. So how can I rewrite that? So that it's something plus something instead of something minus something. Yeah?
Negative 2y plus 3x.
You could do negative 2y plus 3x. Yep, that would work perfect. What else could you do? Nick?
3x plus negative 2y.
3x plus negative 2y. Yeah, you could do it either way. I'll just do it the way Jess said. So negative 2y plus 3x. All right. So Dan, what row in the triangle do I need to look at here?
Third.
Yep. And what's my coefficient, my first one in the third row? Yep, 1. And then Rue, what would come next?
Negative 2y. Oh, okay. Is that parentheses?
Yep.
Negative 2y.
Nope, not the negative 2y yet. The 3x to what power?
That's right.
Yeah, the 3x to the third power. So in the first term, you don't see the second thing in the parentheses. Okay. From here on out until we get to the last one, then we'll see both. So Abby, what's my next coefficient?
3.
3? And Cassandra, my next term after the 3?
The 3x and the negative 2y.
And 3x to the...
30, sorry.
Not third, we already did third.
Oh, second.
Second. So 3x to the second, negative 2y to the first. Okay, Brooke, how about my next term?
It would be 3.
Yep, 3.
It would be 3x first.
Yep, 3x to the first. So now we're at the point where we don't even have to do anything with the 3x except multiply by the number in front. And my last term?
Negative 2y to the second.
Negative 2y to the second. And the last one is 1 times negative 2y cubed. What's going to happen when I do that out? This final answer is going to look a little different than the last two. Yeah.
It's going to be negatives.
Yeah, it's going to alternate positive, negative, okay, because of that negative 2y. All right. So we get 27x cubed. And now the next one, we're going to get 9. Well, let's do it all together. We get 9 from 3 squared. What's 9 times 3? 27. 27 times negative 2. Negative 54. So we just took care of all the numbers. Now we got to deal with the letters. X squared, y. Okay, the next one. We've got negative 2 squared, which is 4, times 3 is 12, times 3 is 36, x, y squared. Okay, and then the last one, negative 2 cubed, what is that going to be? Come on, Ariana?
8.
Yep. So we're gonna we'll just make it a negative 8.
Then y cubed.
Y cubed. Perfect. There you go. So notice positive, negative, positive, negative. Okay, any questions on that? Okay, so that's how you can expand a binomial with using Pascal's triangle. I'm not going to do this one out, but what's going to happen at some point is you're going to get something like this. I just want to know, how do you deal with a power to a power? Yep. You multiply. So anytime you have a power raised to another power, you need to multiply. And that'll come up in this one. so Pascal's triangle, no problem if your row is pretty small, but if the power you want to raise to is kind of big, like 20th power, well, you need the 20th row. So we got to get a better way to generate the coefficients. So to do that, we're going to use a formula, but the formula is going to involve factorials. Does anybody know or familiar with what factorials are? Yeah, I've probably did them in algebra 2 a little bit. So first of all, factorials are only defined for integers. Okay, although you can write a decimal factorial, we're not going to talk about that in this class. So we're going to stick with integers. So the symbol for a factorial is just an exclamation point. So basically, what this means is that if you want to know what n factorial is, it's the product of every number from 1 up to n. So if n was 10, multiply every number from 1 to 10. 1 times 2 times 3 times 4, all the way up to 10. Okay, so the way you would pronounce this is you would say n equals 1 times 2 times 3 times 4. You get excited, you get exclamation point, excitement. Sorry. I'm gonna do it again. Ready? So thus, n is the product of all the integers from 1 to n. Okay, we don't have to keep saying it that way.
Yeah, you do.
Why is it an exclamation point?
Why? I don't know why that's the symbol. I have no idea. Yeah, I don't. I'd have to look up why is the exclamation point used for the factorial symbol. Maybe they've already used every other symbol in math and they say, all right, we'll use an exclamation point. I don't know. But that is the symbol. It's on most calculators, on the graphing calculator. It's under math, probability, and it's the fourth option. So, the definition of a factorial is the product of every number from 1 up to your integer. Well, how do you multiply every number from 1 up to 0? That doesn't really make sense. You can multiply every number from 1 up to 5, or every number from 1 to 20, but every number from 1 up to 0 doesn't really make sense. So, for 0 factorial, it's more of a definition. 0 factorial is just 1. Even the next one's a little weird, but not as weird as the first one. Multiply every number from 1 up to 1. That's like you're just multiplying 1. You just have a 1. That's all you have. And then from here, the definition makes sense. Multiply every number from 1 up to 2. Okay? So what would 2? What would that be? Yeah.
2.
Just 2. 2 is just 2. How about 3 factorial? Devin?
6.
Yeah, 6. So what's happening is it's getting big. It's getting bigger, but it's actually getting bigger very fast. So by the time you get to 4 factorial, now your 4 times 3 is 12, times 2 is 24. And by the time you get to 5 factorial, that's 120. In fact, even if you type in a number like 65 factorial. Now, 65 isn't, it's not a huge number. Like 65, it's not like in the billions or anything. But 65 factorial, it's almost big enough that the calculator can't do it. Okay, just doing 65. I think by the time you get into the 70s, somewhere in the 70s, the exponent would now be in the hundreds of digits long. So it can't do it. So there is kind of a limit to what you can do. But some calculators can do more. I think this one can do it. So if I type 75 factorial, it tells me it's 2.48 times 10 to the 190th power. So some can do it. If you type in a number that's big enough, it really starts to slow the calculator down. It's actually just telling me what I typed in. It's not doing it now. So it's actually frozen. So now I've crashed the calculator. And I don't know if you saw it, but it said the operation may take a very long time. And then it finally just said I can't do it. So it's stupid. Right. So factorials get really, really big really quick, which is why when you have to do factorial calculations, you try to reduce as much as you can before you use a calculator. So I said that we could use factorials to find any number in Pascal's triangle that you want. Any row, any column. Make sure you start with row 0, column 0. So we're all doing the same thing. That's the notation that you use. If you want to find a number located in row n, column r, you write it with a set of parentheses and you put an n on top and an r on the bottom. So now what we could do with that notation is rewrite Pascal's triangle like this. The top number is written like that. That's row 0, column 0. Row 1, column 0. Row 1, column 1. Then we could go row 2, column 0. Row 2, column 1. Row 2, column 2. And I'm going to write that out a little bit more in a minute. But that's the notation for Pascal's triangle the new way, using this symbol. And the way you pronounce that is n choose r. Now that comes from probability, the n choose r notation, because let's say you have 3 things and you want to know how many ways can you choose 2 of them as a group. The order doesn't matter. So blue-green is the same as green and blue. You're just picking a group of markers. So if I had 3, I could pick the blue and the green, I could pick the green and the red, or I could pick the blue and the red. So if I have 3 objects, and I want to know how many ways can I pick 2 of them, if I go to Pascal's triangle, row 3, column 2 will tell me exactly how many ways I can do that. Right, so if we go back, let's just look at this one. Let's say you had 5 objects, and you want to know how many ways can you pick 2 at a time, 2 out of 5. Well, there's 10 ways to do it. There's also 10 ways to pick 3 objects out of 10 at a time. So specifically, when we say choose, we're looking at what's called a combination. Okay, if we were going to do the next section, that's on probability. And in a combination, order doesn't matter. Think of a combination as like a group of people, like a committee. It doesn't matter the order you name the people in on a committee. They're all on the same committee. Unless you assign specific roles to people, then order becomes important. But order is not important for just choosing objects. Okay, so always start with row 0, column 0. So, without going through the proof, because that's a little challenging. What ends up happening is that if you want to do n choose r, you can use this formula. It's n factorial over n minus r factorial, r factorial. If you take a class on probability in college, you'll definitely prove that formula. It's not super hard, it's just not really something I want to spend time on right now. So here's Pascal's triangle written with the n choose r notation. That's what I just had on the other page. Row 0, column 0. Row 1, column 0, row 1, column 1. Row 2, column 0, row 2, column 1, row 2, column 2. And you can calculate any one of those numbers you want by using that formula. Now, I probably would use that formula for these rows, because most people have these rows memorized. 1, 1, 1, 1, 2, 1, 1, 3, 1. You know, it's quicker just to know them. But when you get into like row 30, I have no idea what the numbers are in row 30. I know it starts and ends with a 1. That's all I know. Okay. But if I wanted to know, say, what the 12th column was, I would just use this formula. But you got to be careful about typing these kind of things in, because if I asked you on the test to find a number in row 80, and you try to do 80 factorial on the calculator, it's not going to work. So you have to be a little smart about how you type it in. And that's what we're going to look at next. Well, maybe not next, but soon. So this is showing you the binomial theorem written with n-choose-r notation. Okay, the coefficients are from your exponent, and the first one is from column 0. The next one is column 1, column 2, column 3, column 4. The second to last one is n minus 1, and then your last coefficient is n choose n. The row and the column are the same. The a's start at the highest power and go down. The b's don't have any b's to start, and the exponents go up. So that's all I've done, is just write out the binomial theorem kind of in general. So any questions on that n-choose-r notation? All right, so now we'll practice doing some calculations. So no matter what I ask you to calculate, if I ask you to calculate 3 choose 2, or 6 choose 4, or 9 choose 5, what kind of answer are you always going to get? Yeah?
Just a constant or a single number.
You'll get a single number. Can anyone be more specific about the type of number you'll always get? Yeah? The positive integer. It's always going to be positive, because you can't, think about if you were making choices. You can't make a choice in a negative number of ways. And you can't make a choice in a decimal number of ways. Right? You can't have 2.5 choices. So the answer is always an integer, positive integer. Okay, so let's try doing 6 choose 4. All right, so in that case, Cassandra, what's n? Yep, and r? 4. So it's n factorial over n minus r factorial, r factorial. Now that's small enough you could type it in on the calculator, but I'm going to show you how to reduce it in case you have one you can't type in. So Devin, if you write out the top, what does the top mean?
What does it mean?
Yeah, like let's say somebody doesn't know what exclamation point means.
It means all the numbers up to 6 multiplied.
Yeah, so 6 times 5 times 4 times 3 times 2. You could put times 1, but you don't need to. 6 minus 4 gives me 2 factorial, which is just 2. And 4 factorial, 4 times 3 times 2 times 1 if you want to put it. Now, if you had to do all that in your head without reducing it, it might be a little hard. But what could you cancel out there before you try doing it? Yeah?
The 2's, the 3, and the 4.
Yeah, 4, 3, 2, 4, 3, 2. That's all gone. So you don't need to worry about that. And you can also cancel 2 into 6. 2 goes into 6 3 times. So now your denominator is a 1. That should happen every time, okay? Because you never should get any decimals. So what's the answer to 6 choose 4? Yeah, 15. And if you look at our Pascal's triangle, I think we did that out up to the 6th row, look at the number in the 4th column. It should be 15. Okay. Let's look at 9, choose 5. So this is not one we've done out. We didn't go out to the 9th row. Right, so Scott, could you set up my my fraction for the formula, and then we'll kind of go through after and see what we can reduce.
9 factorial.
Yep.
And it's 9 minus 5 factorial. And 5 factorial.
Yep. So, if you look at the top and look at the bottom, the way you figure out what's going to cancel is look at the biggest factorial in the bottom, 5 factorial. Everything from 5 down in the top is going to be gone. So you have 9, 8, 7, 6. 5, 4, 3, 2 is going to cancel with 5, 4, 3, 2. So that's all gone. Over 4 times 3 times 2. Any questions how I jumped to that step? Okay, now you can reduce this any way you want. 3 times 2 is 6. 4 goes into 8 2 times. So now I'm just left with 9 times 2 times 7. Much easier calculation than what you had before. So 9 times 2 times 7. So we get 126. Okay. Any questions on that one? All right, so what I'm going to have you do with that is ultimately something like this. I want to know the 12th term in this expansion. Okay. 2x plus 3y to the 15th. I would not have you write out all the terms. It's way too much. I just want to know one of them. How many terms would there be if you expanded that whole thing out? Yeah. There would be 16. So to kind of keep track of what I'm doing, I'm going to put 16 little dashes on the screen so I can kind of circle the one I want. So there'd be 16 terms. I want to know the 12th one. But when we start the counting, we always start with the 0th term. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the term that I want to know. So let's start with the coefficient. What would be the notation for my coefficient? I'm raising to the 15th power, and I want to know the 12th term. Yeah.
15 choose 12.
Yeah, 15 choose 12. So we have to figure that out, and that's what we just did before. Now we just have to figure out what's up with the 2x and the 3 to the y. I know they're each going to be part of the final answer because I'm not at the beginning, I'm not at the end. So each one of those is going to have an exponent. Once I know one of them, the other one just has to add up to 15 because the two exponents always add to 15. How can I get the exponent on the 2x? That's what I can do. Huh?
I don't know how to explain it, but wouldn't it be 3?
All right, how do you, you're not sure how to explain it.
Well,
So
you ignore the last one because it wouldn't like exist.
it wouldn't exist there, yeah?
And then you count back.
Yeah, you can count from the beginning or the end, whichever way helps you, but from the last one it would be a 0, 1, 2, 3. Or start at the beginning and say, well, it would start as a 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3. So we know the exponent here is to the third, which means the exponent on the 3y must be... Oh, Brooke.
Is it 13? 12?
Yeah, it has to be 12 because these two have to add together to give you 15. And that's it. So now the hard part is done. Now we just have to do this out. Okay. Does anyone want me to finish it up from here and do that out? This part I could do out the last, well, actually this one's going to be pretty big. 3 to the 12th, it's going to be pretty huge. So it's a question of, do they even want you to do it out that big? It'll say in the directions. But if you can get to this step, you should be good from there. Okay, so any questions on that? So on the test, I'll probably give you one that's in a row like this. It's way too high. It would just take you like 15 or 20 minutes to write this triangle out. So it's too high to do it that way. So you got to do it this way. Okay, just remember, start with the 0th term. That'll keep things on track. Okay, and that's the binomial theorem. Any questions? How about anything in general for the test tomorrow? Tomorrow will be our last test. Yeah.
I just have a question on this one. Like, how does the 2x and the 3y like come into play? Like the answer. Like
the exponents?
Well, like I don't know, cause like, what would the answer be? Like.
So the final answer would be, well, I'd have to do out 15, choose 12.
Yeah.
So that would be 15 times 14 times 13 over. Let's see, that would be 3 factorial, and then the other factorial would cancel.
Okay.
So that would be the first part. 15, 14, 13, the 12 factorial is gone. Yeah, so that's good. Then I would do out 8x cubed. So get that number.
So you multiply it by that.
Yep, multiply that by 8x cubed. And then the other one's going to be pretty big. 3 to the 12th.
And
Y to the
multiply
12th.
it by that. Okay.
Yeah, and then you multiply it by that.
Okay.
I guess 3 to the 12th isn't that big. It's kind of big. So 531,441 times 8. So 4,251,528. That's the number that you get from this part. Times whatever you get here.
Okay.
Any other questions on that? All right. Okay, so that's the homework for tonight. So it's on page 606, and it's 1, 3 through 8, 11 through 15, 17 to 19, and 21 to 25. Okay, I will be after school today if anyone needs extra help. Also, once you take your test tomorrow and show me your homework, your term 4 grade it is done. So hopefully I'll have that updated after you take the test. And then 2 weeks from today is the final. Okay.